You're listening to EE Times On Air, and this is EE Times Current. I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Dr. Jennifer Hasler of Georgia Tech talks about the importance of and progress in analog electronics for AI. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny is talking to Dr. Jen Hasler, a professor in the School of Electrical and Computer Engineering at Georgia Tech in Atlanta. Jen is best known for her work with field programmable analog arrays, or FPAAs, flexible substrates for implementing analog and particularly neuromorphic designs. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Jennifer has been part of the neuromorphic community since the late 1980s. She's been developing analog technology to run spiking neural networks for more than 2 decades and is now looking to make that technology more accessible to the wider community. She's doing this through her group's new Python-based analog synthesis tools. There are links to her work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. We recorded this interview online. Jennifer Hasler, welcome to Brains and Machines. Can you start off by telling me about your technical background? What was your first degree, and how did you get interested in neuromorphic engineering?
I did my first 2 degrees at Arizona State and then did my PhD at Caltech with Carver-Mead. Those are my first 3 of my 4 degrees. I grew up in Phoenix, at least partially. I was very interested in electronics early on. I managed to take some classes at Arizona State while I was still finishing high school. One of those classes was actually looking at some IC level design, and I first met who would eventually become my master's thesis advisor, Alex Akers, who just recently passed away a couple of years ago. He was very enthusiastic on VLSI design, but he was also very interested in this whole new area of neural networks and all of the new possibilities of the time. Particularly this newfound algorithm people were talking about called backpropagation. And then he would often talk about one day there will be multiple Nobel Prizes in this area, which, interestingly enough, we just had one last year. So that's where it sort of began in terms of trying to think about circuits and electronics. And I did my undergrad and master's degree as a joint degree, built probably 25 different ICs by the time I was done. It was an exciting time. From there, I had the opportunity to go work with Carver-Mead, and that was just an amazing opportunity. And it was very fascinating for me because I started outside the neuromorphic community, and then I brought that in with me when I started to work with Carver. So I already understood some of the big questions in the field. One of the other good things when I was at Arizona State is I ended up taking some of my first classes in nonlinear dynamics and computational neuroscience, and Steve Baer was very interested in dendritic computation in spines and related kinds of things. So Carver would get very excited about things he'd seen in dendrites, and I could very quickly continue those conversations, which was amazing.
Okay, so why don't you tell me more about what exactly you did at Caltech? What was your PhD thesis about?
So my PhD thesis, its focus of asking what was learning and adaptation. But the biggest center point was a device which we eventually called single transistor learning synapse, which was the first sort of fully successful case of having a single element. It was a floating gate element, which meant that you could actually look like it as a transistor, but you could set it up to store charge in all of the capacitive networks. It's really kind of a neat structure. But we did this entirely in standard CMOS. Today, it's very common doing embedded double EEPROM memories in silicon, but at the time, there wasn't anything there. We also developed it because we wanted these to be synapses. So we built an element that could not only do computation, but it could store an element in a non-volatile way. It could be programmed, it could be adapted, and could be at very, very low power and small energy. And this turned out to be a really big deal. We could build it into a crossbar, have almost perfect selectivity, so I could program one element and measure one element perfectly. And it was really the first, as we know, of crossbar devices today. The concept is still arguably the leading idea across all of this thinking now 30 years later. It was an incredible run. We looked at a lot of questions in how do you do adaptive structures. So people often talk about embedded devices as I can only read or write maybe 100,000 times, and that's a good number. We were looking at trillions and trillions because if you needed to do adaptation, this is what you needed. This was a key concept. So we spent a lot of time understanding all of these properties, understanding fully adaptive circuits, as well as getting deep into the device physics so that we could actually model all of these concepts, like, say, hot electron injection. At the same kind of level, we were modeling gate and drain currents of the transistor. So it was a really neat time. It has been a platform for so many of the things that we've done over the last 28 years here at Georgia Tech.
So you are best known for your work with field programmable analog arrays, or FPAAs. These are kind of the equivalent of FPGAs, but analog. Can you talk about how you started working in that area and what motivated you?
Yeah, so the FPA field was an interesting one that we started while I was here at Georgia Tech. When I was first here, we managed to do many different custom devices, a lot of very efficient computation. We had proven Carver's hypothesis that analog should be, 1,000 times more efficient than digital. And we were very careful about that, and then developed compute and memory. That was 2001, and continued to develop that ever since. And so we were looking at across different applications and so forth. It turned out that two of my PhD students, Tyson Hall and Chris Twigg, they had TA'd a bit at Georgia Tech and were key instrumental players on bringing the FPGAs into the classroom. And they did an amazing job of developing what was a sophomore level course. And this was a day when FPGAs were really not in the classroom yet. So it was very cutting edge to do this. And after doing that, they were also like going, well, wait a minute, can't I do this on the analog side? And so that's where it started. You can see the first time we published on this, and we used floating gates because there's huge advantages to do so.
For people without an electrical engineering background, can you explain what a floating gate is?
A floating gate is basically what we would use in standard CMOS to be able to store, charge, compute, and adapt a device. Floating gates are the core element behind all double EEPROMs, all flash memory structures, and an array of other structures. So if you have a memory stick, it's going to be all double EEPROM. Most hard drives on computers for the last nearly a decade now are almost entirely all flash drives. So it's pervasive in so many places, but it's a structure that's very natural in just using transistors and capacitors of some form.
So if I understand correctly, these have the advantage not only of being analog, but also being very small.
Correct. The devices are very small in the sense that it's just a transistor and a capacitor or two that are similar size of the transistor. And people typically program them in a digital form, but it turns out that they can be programmed in analog form too. The charge on the gate doesn't know whether it's digital or analog. And so it works really well in terms of being able to hold charge. So continuing on the FPA story, we had the first couple of publications, 2002, 2004. And one of the things that became very interesting as we started to develop it in both the academic side and discussing on commercial perspectives of what's possible is that we started realizing that all of our routing fabric, basically the way that you connect all your signals together in an FPGA or in an FPA, could be actually used for more than just routing. Typically in digital, you would assume that all the switching is there to just give you the configurability, but otherwise it's just kind of dead weight. On the analog case, what we started to realize is that we really have analog crossbars that we could program at high precision. So we could actually use the switches for computation. And not just like a little bit. We could use it for like emulating a resistor. We could use it for some other circuits and bias generators and so forth. But we found out we could actually do like vector matrix multiplication in the routing fabric. We found out we could do resistive networks for energy minimization in the routing fabric. We could build some dendrites in the routing fabric. We realized there was so much possibility, and in fact, it changed the way we think about the architecture. Sometimes you realize the elements that you're selecting between may be more the boundary conditions of the circuit rather than just a selection of different menu items. And this turns out to give you a tremendous amount of capability. It also means that the efficiency in terms of area and resources that you have on an FPA, you can use them in a very large amount of elements, but it also says I've got a very fine-grained structure, which really enables the creativity of the user to do all sorts of different things with it. It's not saying, okay, here is a selection of menu items and choose them, which is already very nice. But it's saying there's probably circuits and creativity that we didn't ever intend when we built it, that somebody else will see and go, I can build it this way. And that's, I think, phenomenal.
So the FPAAs, as we've discussed, can be thought of as a simulator for analog designs, but also can be used to implement analog designs. Is it a problem for you that we're training fewer analog designers than we used to?
Are we needing to train more analog designers? The answer is clearly there is a need. When I started at Georgia Tech 28 years ago, everyone said we had a 10 to 15-year lag of the number of analog designers that we needed. No one has said that the problem got better in 28 years. And I think most people actually don't realize how much possibilities there is in analog design. I think it's also very important because it is a subset of that group who could do sort of analog computation and some of the more system level design. So when you're already talking about a small number, I think it was about 10 years ago, IEEE thought there was maybe 3,000 analog designers worldwide. You get to pick from a subset of that group in terms of doing some of the more larger neuromorphic design kind of approaches. And so we clearly need more. I think more across every space would be helpful. No problem getting jobs. People will hire you quickly. And I think there's a lot of really great creativity that's possible there. So more analog designers is important. The other part on the FPA side is that we definitely have paid a lot of attention to the tool aspect, sort of because of our own success. We would often get chips with 1 million devices in it, or 1 million programmable parameters. That's wonderful. It's great. It's also, you're not going to do that by hand anymore. And so we had to have some tools to make this work. You talk about analog tools, particularly even 10 years ago, and everyone's like, it's just not possible. Everyone just did layout and raw, bare metal kinds of things. And sometimes you innovate because you have no other choice, because what else am I going to do? And so we started learning how to build tools to do this. And part of the philosophy, and this was helpful from some of the commercialization interactions that I had had, is that it was very clear that I wanted not just analog designers to be able to use it, although that's critically important, but I wanted people who were more system designers and even potentially application designers. And I had people in mind. It's always good to picture somebody when you're building a tool, like, I'd like it to work for this person. And you start to realize that it is actually possible to abstract things enough to do that. But again, the whole concept of analog abstraction was a thing that no one really thought was even possible. I mean, digital, you go, well, I have NANDs and NOR gates, and I have multiply and adds, and isn't that wonderful? Analog, it's just too hard. You can't do it. Well, when you're faced with a problem, you got no choice. You start thinking about it and you start to realize it's a little more complicated, but it's not that bad. So those are things that were very, very helpful and gave us the ability to say, well, FPAs could be used by people who are not traditional analog designers, although certainly it helps. And anything you bring to a system and your experience can be valuable. And so the analog design certainly is great, but people bring different skills. And it got us started to think about tools. I think today, in my research group, we spend probably half our time thinking about tools and tools-related issues, which is not what I ever intended when I graduated from Caltech, but it's where we are.
So leading on from what you were just saying, who are the people you have in mind when you design these tools?
So in digital, we're used to having tools that, you can start from a high-level definition and work your way down. So people are used to writing things in different levels of Verilog is a typical language, and can synthesize it to an FPGA often, but it can also be synthesized down to custom hardware definition that then you could fabricate that chip and continue. That did not happen overnight. It took maybe a decade and a half to really make that work, and starting from the late 80s to about 2000 to be really effective. What's nice about it is when you try to think about who the users are, they're typically going to be not necessarily people who are deep digital circuit designers. What you want is people who can think about digital architectures, people who aren't even really thinking about even too much of the Verilog side of it. Maybe they're even higher level and they can just compile it down. And so the question is, could we do something similar on the analog side? And the reasoning for that one is if you're too close to the bare metal, it takes a lot of time. There's lots of flexibility, but it takes so much time to do the design. The last set of FPAAs we did, which was the system on chip FPAA design, took 7 PhD students and myself 6 months to design. It was a large effort, and from an academic space, that's a very long effort. So that was one of the things that was already in the back of my mind, how to get that better. But at the same time, if we can then allow higher level users to say, okay, not only can I design things and they could target an FPA, but if they built that design, maybe it could very easily flow to an IC. So not necessarily someone who is an analog expert even, it could be abstracted enough. So as long as they can understand like a couple basic continuous time processing ideas, they're good to go. And so that means I go from needing the people who are, say, analog designers to people who do signal processing. There may be people who are signal processing with a knowledge in machine learning. And so they don't have to be all the way down, but it's enough. And they can say, hey, this is the chip I want. I can start exploring it. I could create things and build that. So you go from maybe having 3,000 to 4,000 people in the world to maybe a couple million people in the world. That changes your adoption very quickly. And so there's a really huge opportunity. And I think once people start getting excited about it and using it, that will only grow further. So that's kind of the mindset that we're looking at. And how do we get a wider adoption of these concepts and these tools?
If you wanted to target a couple of groups who could really use FPAAs, who would they be and what would they be trying to do?
At one level, one could ask an interesting question digitally going, well, what are the really good applications for FPGAs? And people would go, well, they're used ubiquitously in tons of places. And that's true. It does turn out there's a couple of things that they really are aimed for. They have the ability to be general enough, they're wider all the way through. In fact, if you're curious, I think the biggest thing they're aimed for is a lot of the network routing concept. That was the first killer app for FPGAs about 2002 or so, which took them 17 years to get there. So I also understand that takes some time to get all of that right and interacting in the market and a lot of different dynamics there. So for the FPGA structures, they clearly could actually play in many of the FPGA applications and so on. But where do they play best? They play best in areas where you're dealing in low power computation. You might say these are devices at the edge. These are devices that we put in our handheld structures. Very, very important to be looking at that. For a place where I want to use microwatt level or milliwatt level of power, this is where things are incredibly valuable because there's just not a lot of other solutions and certainly not any programmable solutions in those spaces typically. That would include having end-to-end solutions, which is I want to be able to go from the sensor all the way to the classified output, which means that there's going to be machine learning and what I like to call embedded machine learning. We've been using that term for about a decade or more now. But it has to then also have all the front end of it too. So if I'm doing an acoustic classifier, I have to be able to go from a microphone, go through all the other stages, build that into whatever my classification network is, and then proceed from there. And there's certainly some architecture questions of what is more advantageous, what is not, but that's what we're looking at. That's where a lot of the building blocks are. Same sort of thing if I want to take an image sensor and work all the way through that. But it would also be a case of saying, imagine I have, 32, 64 antennas, and I'm doing a beamforming structure for MIMO applications, which we use everywhere around us. And there's a range of people who are interested in this problem, clearly. But there is a lot of things that you could imagine in any one of these spaces where you're going, I need to have a sensor, and I would do the computation. One of the things we've realized architecturally that you really want to run at the speed of your data coming in. There's actually something I remember originally hearing Carver making a sort of offhand comment about that was an incredible little nugget of wisdom, typical for Carver, who's just an absolutely amazing person. So if we're doing image processing, you want to be able to run at the speed of the image sensor, whatever it is. And so if it's scanning all the pixels off, if that just is your image sensor you want to use, and you really want to run with that data rate, because not doing it means you have all these intermediate memories, you have all this communication bottlenecks, all the memory is costly, you just got to avoid that. But these FPAs work in all of these ranges in any sort of sensor or actuator-driven problems. And it also doesn't mean that you wouldn't have any digital structures on. In fact, our FPAs do have some digital structures. There's a processor on there, which we find extremely useful for interfacing to the rest of the digital world because it's not going away. On the other hand, you don't want your analog looking like a coprocessor. That's usually where you get in big trouble because there's costs and all of the constant data changing back and forth, and you lose the advantages of both the digital and the analog computational modes. In the early neural network community, the late 80s and early 90s, we understood this problem. We usually call it the worst of all worlds problem because that's what you're getting. So we often try to be very careful and methodical to use an architecture that's effective such that the whole thing works. And the FPAs really give you that opportunity without having to do like detailed IC design in the process.
I'd like to give you the opportunity to tempt people to see that the tools that you're developing are going to make it easier for them to make things that they weren't able to make before. So can you just talk me through your target market? Who do you want to use the tool? What is it that you want them to do? How is it the same as the workflow they've used in the past? And how is it different?
So I think the typical person who's doing system design, I think this is where the tools are being aimed, and I'd be remiss by not saying there's a whole group of graduate students who've been doing tremendous work on this. And again, the tools are what enable the next generation of things. It's just incredible. I think the goal is it should hopefully feel somewhat similar in a form, in the sense that, if you're talking about what is called high-level synthesis, you'd like to be able to start off with, say, a Python set of subroutines and definitions. And in some sense, that will feel similar to what you might do in a digital space. The difference would be is that some of the functions may look a little bit different, and some of the parameters of the functions and some of the variables when you're optimizing the tool flow might look a little bit different. For example, you might be asking, what is the frequency of the input signals versus saying, what is the sampling rate? It's a small detail, but it makes a big difference. So there's a few things like that you definitely want to make sure of, but things that in theory a classical electrical engineering education would have taught you. Now, some users that might make sense. Some users might go, I don't have that, and hopefully can build some of those references over time to kind of give people that ability to do that. I know personally, I've felt very strongly about also doing a lot of open source things, including my lectures, and they're all open and available on YouTube and so forth. So if that helps people go, oh, I need an hour of primer, we're like, well, okay, there's a few lectures, go look at them. But the thing is to keep it a small amount of material that's required.
So as a teacher, I know you've tested these systems and models on your students. So maybe you could talk a little bit more about that and how the students find it.
We do use the FPAs in classes, and that has been incredibly helpful. And that does also mean we get to use the tools we developed. And as we keep building new tools, we'll continue that. The merging of education and research is something that I learned a lot from Carver and how to do that effectively. He very strongly believed that you really need to touch and feel what you're building and what you're learning about. And you have the experiments that lead the pedagogy of the teaching, right? Basically how you're teaching it. So that was invaluable. And that is one of the approaches that we use a lot here, both in undergraduate and graduate courses. We have had a lot of really interesting experiences from the students over the years. I think once you get past anytime they have to do something experimental, they're like, oh, that's a bit more work. Because theory in a classroom is easier than experiments. There's no way around that. But experiments teach you so much more. Once they get over that point, they actually find what we could do rather interesting. And they also completely miss that there's all sorts of things underneath the system that they didn't even realize was there. People will realize in our tools that there's some graphical structures that we use for class, and they will double click on a value and put in the parameter to 3 or 4 significant digits and just hit go, and they're like, wow, it's close. I wish it was, it's maybe a couple % off of what I expected. Having absolutely no idea that this is all analog and it's actually real. And when we talk about like a few weeks later exactly what we mean by precision and what the challenging questions are, it's been incredible to watch students only after they've been using things for weeks realize, oh, that actually is a hard problem. oh, wait, nobody else does this? Oh, I had no idea. And it's one of those things that, I remember from Carver saying, it's amazing when you're teaching because the students, they don't know all the pain of the past, and they can begin to be creative of where they are now. And I've seen that happen again and again. So the students in general respond to the tools fairly well. There sometimes people will say, hey, this looks like commercial tools. Who do I talk to for tech support? And we have to remind them, like, no, actually, they're not commercial tools yet. But overall, the experience has been, I would say, fairly good.
So one of the really important developments you've made in recent years is this concept of the standard cell, which is a way of organizing your analog electronics so that they can be used most efficiently. So can you talk about what they are and how they work?
So the standard cells have been an amazing part of the custom synthesis part of the approach. So we started this trying to say, well, we understand some of the FPA compilation and targeting. We also had experience building many different generations of FPAs, more than 20 years of looking at this and developing the tools to target it and choosing what made the most sense. But a lot of the ideas were, okay, so what should the standard cells be for an analog structure? Now, again, this is one of those cases where people were just like, this is crazy. No one would even think about this. And the first starting point in an analog space is that this would require you to have different device geometries for every single possible configuration and bias current and so forth. So we started with this saying, well, wait a minute, we already use things that are programmable with all the floating gates. So how much does that actually simplify the circuits and the topologies? And it turns out it simplifies a tremendous amount. The second thing is that we realize is that people use certain circuit topologies like very high gain amplifiers because they're getting precision based on feedback elements that are passive elements that they feel like they have better control over. Well, if you have precision with the programming, you don't need the precision in those forms necessarily. You have a design choice now. It frees up your design to saying, I don't need to do certain things I always do in classical analog design because I can get precision with the programming, with the floating gate elements. And that turns out to both simplify the number of elements you need, as well as simplifies a lot of the different transistors, sizes, and so forth, particularly when you're operating most of your transistors in subthreshold anyways. After 45 nanometer and below, you're already getting effects like velocity saturation in the diffusion current. So you have only really a subthreshold and modified subthreshold region at all. And so therefore, all of the things that we developed over decades in the whole neuromorphic community turn out to be extremely valuable now. So all of this comes into play as we build out the standard cells.
Can you talk through the level of flexibility of the chips you can develop using your design tools and standard cells?
So a digital ASIC chip, you actually can have very much fixed function, but there are also the ability to do programmable structures in a digital ASIC chip because you would have SRAM. You could also have other kinds of memories in there. It's possible, for example, to synthesize an entire microprocessor with SRAM sitting next to it. So clearly there's programmability there, but there's obviously some structure that you're building. You could actually imagine doing ASIC tools to build a new FPGA. This is also possible. But you could also use something that's completely fixed function. The nice part on the analog side is that now with the analog structure, I could also build something that is programmable to parameters where maybe I program them once just coming off the assembly line and I'm done. Because again, I know that I'll have very good accuracy for the lifetime of the part. Or I can do things where I can have some limited level of programmability. Or I could do something where I could use these same tools to go create a whole new configurable fabric. This is a very important aspect that we're working on right now, using these tools. So I think that entire range that you see in the digital space, we're talking about also in the analog space as well. But the fun part about this is most people do not think of analog and programmable in the same sentence. And the fact that I can give you the same entire range, the same way you would have in a digital space, is rather remarkable. For a whole group of people, they won't have to worry about the analog complexity. Now, if you're an analog designer and you want to really fine-tune some things, you could. If you're an analog designer and say, hey, this gets most of my application, but I'd like to build a couple of my own special standard cells to put in my synthesis flow because I want to do something interesting. I need a special, say, neural sensor for a system. It actually could be built into the flow. In theory, you could do this digitally too, but almost nobody usually even thinks about it anymore digitally.
So this design tool called ASHES is open source, yes?
This tool is open source, and we've made a strong commitment to be open source where we can. It's very tough to do that with IC design files and related things, and we're working through a couple different options to figure out how to find a way to make this be available. The same thing is also very important in terms of making FPAAs available. That's actually developing quite well. Again, I've had experience doing commercialization, so we actually launched out, at least initially, a sort of startup to try to make these accessible. That would have been like 2017 when we started it. It eventually got acquired in with a company which is called Akika, who also learned how to make this work for older, very small anodyne configurable chips. And so there's a large opportunity there. They are enthusiastic to make these commercially available. I think that's ramping up very quickly over the next couple months. So I know people are already buying them in very limited numbers, and hopefully that grows very quickly. I'm very excited about that opportunity and how that can continue to expand. The same thing on the synthesis tools is people having the tools, hopefully having enough that they can start to work with. And then we're working on figuring out a way that you could take that and then find some way to be able to synthesize it and get to an IC. Of course, it's a very complex problem, but it looks like everything is possible. We're just trying to work through these options. And so I imagine over the next year or so, we'll be seeing more of that, particularly with some of the other new chips and things that are going to be coming out over the next year.
In terms of trying to make your work more accessible, I wondered if you'd ever thought of working with applied brain research and the neural engineering framework, or NEF, that they use to create cognitive networks. I know they supply accelerator boards with interesting neuromorphic hardware platforms that can be compiled with their systems, and I wondered if you'd thought of an FPAA as being one of them, potentially.
It was interesting bringing up the NEF part, because we certainly, obviously, through the neuromorphic community, good friends with several people there. This is very much an interesting question, and how to start to build the intermediate neural representation types of languages. I think the very first one that was done at a Heidelberg group, which was PyNN. And I think that was one of their great successes, was starting to do that. It's been something that we've been very excited about. We actually do internally try to make those connections. Between there's the neural intermediate representation group of people. We really want to be able to unify these concepts, so that way people can be thinking from a neuralist perspective and how you put things together. Initially with the tools, we've been focusing it, I'd say, more initially on analog computing and analog signal processing, because that's a little bit better defined of what we actually need. But always with the eye of, this is all going to work for the neuromorphic community too. It's trickier in the neuromorphic community because there's a lot less understanding of what is the actual computations you want to do. So that's kind of important to build some of the tools in the tool flow. But everything seems completely possible to me, but it's just going to take a little more time to get that right. But we're very quietly in the ground floor with all of these groups because it matters tremendously. And if there's a group I've missed, I'm also very interested in having those conversations.
So finally, thinking more widely about neuromorphic engineering, are there trends outside of your own work that you think are promising and you'd like to see more of?
I'd like to see a lot more than dendritic computation go forward. I think that's important. And looking at doing more cortical kinds of computation that could be valuable for engineering applications. We have been involved in that, so it's not something we're not doing. But I do think the space of neuromorphic computation that I would say is temporally sparse is very critical. It's been very clear when we did the neuromorphic roadmap paper 12 years ago that the sparsity of the neural code is essential for the energy efficiency in the brain. Without the sparseness of that code, you don't get the energy efficiency. You don't get the 10, 20 watts of power. So those are very critical points. And I often frame it as I really want to see someone build a cortical column of, say, 10,000 or more neurons, realistic neurons, actually do an important engineering application. And that has a lot of different challenges to it, one of which being, well, what's the computation being done? I think this is where we've been enthusiastic when we've been able to build connections between dendritic processing and HMM classifiers. Gives us at least a framework. Is that the best model? We'll see. But at least it's a model. And if you don't have any model, then you're really struggling how to even think about an application. And therefore, you're also struggling understanding what is the brain actually computing. We think this is all important and energy efficient and the spikes matter. The question is why? Why in any sort of computing approach? And I feel very strongly that it's true, but I also understand that that doesn't mean every single thing needs to be spikes. So understanding that balance and using spikes where it matters. And it does seem to be in general that the sparse temporal rate kinds of codes is the most critical question. And that opens up a range of applications, but it's very challenging because it forces you out of your comfort zone of so many of the algorithms that are developed today.
Jen Hasler, thanks so much for coming on to Brains and Machines.
Thanks, Sunny. So in this world of massive production of papers, I really enjoyed the maturity she has as a researcher. She shows patience for results to come out in years of studies, and I loved it. And I absolutely thank her for her open source lectures. It's really important. And now we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hello, guys. Nice to be back again.
Hey, Ralph.
Okay, guys, so the first question is not going to be specifically technical, but it's really a curiosity, and I'd like to hear your insights from this. So we all know that this year, 2024, the Nobel Prize in Physics went to John Hopfield and Jeffrey Hinton. And she mentioned it, right? And they won it for foundational discoveries and investigation that enable machine learning with artificial neural networks. So what's your point of view in this? I'm super curious, because what I think is that we are shaping research leading towards industrial research. And I don't know how good it is, but I want to hear your thoughts.
I just want to chime in and say that I'm not sure that it's necessarily a good idea to be giving prizes to people who are making money in this way. I think these prizes were set up to support research in a particular direction in pure science. And I think that although I don't take away any of the achievement of what Hopfield, who I was a fan of back in the late 80s when I was writing about optical Hopfield networks, I don't want to take away any of the achievement of the restricted Boltzmann machine and all of that, but I'm not sure it's appropriate for it to get the Nobel Prize in Physics, personally. And for the chemistry one, of course, was DeepMind. I kind of feel the same thing. Although I think even Ralph and I have maybe had this conversation before that, sometimes tools do win these prizes. Personally, I was slightly troubled by it.
Yeah, and I don't have the same troubling perspective as Sunny does. Look, I mean, at the end of the day, there's what one can see as useful science, and then there's useless science, which is the pure science that goes behind it. And at some point, they become useful science, right? Because people develop an application and so on. So the mere aspect of commercialization that comes out of some of the things that we do, I don't think is a negative. I think is inquiry and curiosity that folks have at the very beginning is what drives the questioning and the development. And ultimately, there might be an application that makes money. It's okay. I don't have a problem with it.
One other thing to say is that I met Jeff Hinton a couple of times back in the day. And one thing I would say is, to me, he always really seemed like a true believer. He was working away at this for decades before anyone even, we noticed him in the field. But I think for him to be getting recognition now is not a bad thing. But again, the fact that he's getting this recognition after, presumably earning oodles of cash at Google and such, I don't know.
I mean, I do think that the Hopfield net, all the theory that went into understanding capacity of associative memory and the oodles of students that came out of that and what they went on to do, clearly the science behind it is deep. And all that came out of understanding it, is very physicsy. So in my view, it fits the bill, right? One place that one may have a bone to pick is that maybe not everybody that should have been recognized were recognized. And I know that there's a limit on the number of awardees that can be given, the prize at any one time. But there are other folks who did a lot of fundamental work, especially on the backprop work, Chinovsky, with the net talk and so on, that maybe should have also been recognized. So that's maybe where I have a little bit of disquiet, if you will, but I don't have a problem on the commercialized side.
One note on that is I have heard Jocelyn Bell Burnell, the astronomer, speak about not winning the Nobel Prize for pulsars. Because she was a PhD student at the time, she wasn't allowed to get the Nobel Prize. And she said, actually, it worked out fine in the end because she won every other prize that it was possible to get. And so it actually worked out fine. So she said, don't feel bad for me.
It's good to hear.
The second question that I'd like to ask you refers to a quote from Carver Mead, where he says, you really want to run at the speed of your data coming in, which I found it really nice. We might want to say that FPGA is a field programmable gate array and FPAA is a field programmable analog array. Therefore, what she says is that traditional AC designs involve significant overhead, including fabrication costs and delays and a need for specialized knowledge in analog circuit design. And FPAA somehow mitigates these challenges, yet we live in a predominantly digital world. So I want to ask you a question that I usually receive during my talks. How can we explain the holding back of the widespread adoption of analog computing? How can we explain that we still don't use it that much as it should be after 20 years?
So one of the things from my perspective is that Jen and I have been talking about her analog arrays for at least 20 years. I went to her lab, I'm sure it was in the late 90s or very early 2000 at Georgia Tech. And I think there are a bunch of issues related to usability by people who are not in her lab that are being sorted out, hopefully now, but that were not sorted out for a long time. And I think it is just harder in the analog domain to make things that are consistent and interoperable. And I'm really interested in this new approach that she has, these cells of different functionality that she creates that allow you to have some of the benefits of analog while also having the benefits of being reprogrammable and reconfigurable. So I think it's a nice step forward, but I think it also shows you the fact that it was a little bit, what's going on with the field programmable analog arrays? That's a good question. Where were they all that time? They were in Jen's lab, but they weren't really anywhere else. And I think that just shows you how usability is so crucial to something taking off.
Yeah, and I agree with everything that Sunny said. I think being a person that has also played with them, has been trained even through the neuromorphic workshop in Telluride over the years to use them. I've had students to try them. It's always been difficult. Right? It's never been as easy as one would hope, and not as easy as FPGA, right? Those guys are easy to use, once you know HDL. So I think that has a big component. So the tools that she's talked about and the tools that she's developing, the paper that's coming up, will hopefully move us a little bit closer to the ease of use. And clearly from a digital perspective, floating gates, which is the basis of all the FPAA technology, is being used extensively, right? She mentions it as being part of our SSD drives, EEPROMs, and so on and so forth. So if it can be it's so well adopted in those domains, why shouldn't the analog part be easily adopted as well? But again, then I'll make a switch and say the difficulty as well has been in form of what the application space is, right? So the analog element, as you said, Giulia, running at the speed of data coming in, that is where the analog processing, analog signal adaptation is really useful. Computation, on the other hand, which is the remainder of the world, right? Once you move beyond the sensory epithelium, then it's all computation. That is massive space where all the digital application lives. So there's a lot more of an ecosystem, I guess I would argue, there than there is for the analog front end and the analog back end, which is, the communication back to the world. So it seems like there is just a much larger ecosystem in between the analog end stops.
A quick note I would make about the paper that we talked about. So Jen very kindly gave me an advance copy of the paper, but it should be out by the time people are listening to us in the podcast. So I'll make sure that we link to it in the show notes.
Yeah. So I thought that Jennifer's discussions were pretty interesting, especially starting from her history with Lex Akers, who I remember, again, one of those folks who you meet along the way. I was a student when I first met him, when he came to Telluride a couple of times, and also worked with a number of other folks in the field. So seeing that trajectory leading all the way to Carver's lab and then for Jennifer to continue the work, that was also an interesting arc, if you will, in her trajectory. The other part that was hit on pretty well was the complexity of dealing with floating gates, why tools are super important, and the connections with NEF as a potential way of programming at a higher level and being able to then just compile down to the standard cells in the type of technology that she invents and makes available to the community. That would be another area that I think would be particularly useful for us to make it more adopted. She also mentions the importance of having analog designers and the fact that there's a lack of analog designers in the world. That's something else as well that I think should be played up, and for us to develop more analog designers as part of the education system. And it turns out that digital circuits at the cell design level is actually an analog design paradigm. So there is a lot more that analog designers can provide rather than just the signal processing side. And the last part that I want to say is the adaptive element of her circuits is really useful. It's something that has not been necessarily fully exploited. I remember back, when NeurIPS was just beginning, we had examples of how you can apply the floating gate paradigm to learning and continuous learning and adaptive learning to real world problems, but haven't seen too much more beyond that. So that's another place I think where her work could be really useful in the future.
She mentioned the fact that working with neuromorphic computing is forcing you to be out of your comfort zone. And I think this is really important and really nice. And this is the reason why we don't have all of these engineers that want to be so out of the comfort zone. The last thing, I would like to close with one quote from this interview that I found beautiful. Students don't know all the pain of the past, and they can begin to be creative from where they are now. And this is amazing. So I think this is a great place to stop today. And thanks, Sunny, again, for yet another great interview, and Ralph for your valuable comments as usual. And in the next episode, Sunny will talk to Terry Senowski, the Francis Crick professor at the Salk Institute for Biological Studies, who has been thinking about models of the brain and how to implement them for more than 50 years. We hope you will join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Dr. Jen Hasler. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript, along with direct links to other stories we've mentioned and other resources. Thanks for listening.